Hi, my name is Abanti, and today I will be presenting SAGA-Bench Software and Hardware Characterization of Streaming Graph Analytics Workloads. This work has been done by UC Santa Barbara in collaboration with Intel. The talk will be divided into 4 sections. First, I'll talk about the nature of streaming graph analytics workloads and their unique challenges. Second, I will discuss SAGA-Bench, our developed open source benchmark for these workloads. Third, I'll talk about software level characterization of different data structures and compute models in streaming graph workloads using SAGA-Bench. And finally, I'll discuss our observations from architecture level characterization of graph update and graph compute phases in our workloads. Let's get started with the first section where I will talk about streaming graph analytics workloads and their unique challenges. Streaming graphs are critical in multiple application domains such as financial fraud detection, recommender systems, and social network analysis. This is an overview of what a typical streaming graph system looks like. The input to the system is a stream of incoming edges, and once they enter the system, they undergo sequences of 2 main operations. The first operation is an update operation, which basically means inserting or updating these incoming edges into the graph data structure. And the second main operation is compute, which means performing some kind of algorithm such as PageRank on the updated data structure. And the output after these 2 main operations is the freshly computed vertex values. Now, streaming graphs deserve to be studied separately because they possess some unique challenges and unique differences from static graph workloads. So in this slide, I explain what those challenges and differences are. The 2 diagrams on this slide represent the static graph computation workflow labeled as A, and B is the workflow of streaming graph analytics. So there are multiple differences between the workflow of these 2 workloads. The first difference is that in static graph scenario, we build the graph once, usually in the well-known compress parse row format, and then we perform computations again and again on the entire built graph. In contrast, in the streaming graph scenario, what is done is repeated updates and computes on batches of incoming edges. The second key difference between static and streaming scenarios is the following. In the static graph analytics scenario, the optimization goal is typically the execution time of the compute phase. However, in streaming graphs, the optimization goal is more of real timeliness. That is, we want low batch processing latency, which involves both the latency of performing some updates, edge updates, and also performing some computation. The third key difference is that in the static scenario, the graph update is a fixed one-time overhead. It is sort of like a pre-processing. But in streaming scenario, the graph update lies on the critical path. It is happening online and it cannot be considered as a fixed one-time pre-processing overhead. In terms of prior work, at the software level, there are multiple existing standalone streaming graph systems, but what is lacking is a systematic study of the different software techniques, that is, the different data structures and compute models that are proposed across these systems. At the architecture level, there are multiple interesting papers and optimization techniques which target static graph computation, but streaming graphs remain unexplored at the architecture level due to 2 key issues. The first is immature software techniques. So the data structures and compute models for streaming graph applications are still being developed and proposed. And the second issue is the lack of open source benchmarks, which makes it difficult to perform effective architecture level studies. Motivated by these shortcomings, this work creates SAGA-Bench, an open source benchmark, and performs systematic software and hardware characterization of streaming graph analytics workloads. Next, I will move on to section 2, where I will talk about SAGA-Bench in details. SAGA-Bench is a benchmark developed in C++, and it puts together different data structures and compute models for streaming graph analytics on the same platform for systematic characterization. The goal of SAGA-Bench is not to be yet another competitive streaming graph system, but to provide a fair and systematic performance analysis platform for software and architecture studies. The code for the benchmark has been open sourced on this GitHub repo. SAGA-Bench has a wide scope and can be used for multiple purposes. It can be used for software studies because SAGA-Bench provides a common platform for the performance analysis of different software techniques such as different data structures and compute models. It can also be used to perform architecture level studies. So it's an open source tool for studying architecture level bottlenecks in streaming graph applications. And the benchmark is also very extensible. The API of SAGA-Bench is general enough to accommodate future software techniques. I will quickly go over the contents of SAGA-Bench. Currently, the benchmark supports 4 multi-threaded data structures, Stinger, degree-aware hashing, and 2 different implementations of adjacency list. The first one is a shared style multi-threading adjacency list, and the second one is a chunk style multi-threading implementation. The benchmark also contains 2 different compute models, the incremental computation model and the recomputation from scratch model. And 6 well-known algorithms have been currently implemented. They are breadth first search, connected components, max computation, PageRank, single source shortest path, and single source widest path. All the 6 algorithms have been implemented in both the incremental and the from scratch computation models. Some more details about the data structures. They have been chosen to include variations in 4 different features. The first one is edge update mechanism. So to study the effect of the update technique on update latency, SAGA-Bench contains a variety of update mechanisms, such as hash-based update in degree-aware hashing, update in memory contiguous vectors in the adjacency list, and also update in coarse-grained linked lists in Stinger. The second feature is intranode parallelism. Stinger supports intranode parallelism in edge updates, whereas the other data structures do not possess this flexibility. And this allows us to study the benefit of this extra degree of parallelism. We also look into multi-threading technique. We implemented the adjacency list data structure in both the techniques in order to understand their impact on the update latency. And finally, the fourth feature is traversal mechanism. So the graph data layout and compute latency are strongly tied because a basic operation of vertex-centric computation is neighbor traversal for vertices. So the data structures in SAGA-Bench support a variety of traversal mechanisms in order to study their effects on the compute latency. SAGA-Bench currently supports 2 compute models. The first one is recomputation from scratch, and the second one is incremental computation. The difference between the two is the following. In the FS compute model, each batch treats the updated graph as a brand new graph data structures and begins the computation from scratch by resetting the vertex properties to initial values. In contrast, the incremental model reuses old computed vertex values from the previous batch and computes starting from the affected vertices in the current batch. So this kind of incremental models in multiple cases helps to make the computation faster in streaming graph scenarios. Next, I will move on to section 3, where I will talk about the software level characterization of different data structures and compute models implemented in SAGA-Bench. The experiments are carried out on a dual-socket Intel Xeon Gold server with a total of 64 hardware execution threads. For the methodology, we first shuffle the data sets and stream in batches of 500K edges. Second, since streaming graphs are evolving over time, we try to capture this evolving behavior with 3 representative data points, P1, P2, and P3, which indicate the early, middle, and final stages of execution. And finally, all the experimental results are represented as averages with 95% confidence intervals. We choose 5 different data sets ranging from about 5 million to 500 million edge count. And the batch count column indicates the number of batches streamed into the streaming graph analytics system for that particular data set. For the software level characterization, we want to answer a few key questions, such as which data structure is the best, which compute model is the best, and what is the latency breakdown between the update phase and the compute phase. For the first question, the main takeaway from our characterization is that the best data structure depends on the per batch degree distribution of the graph. For the experimental results on this slide, the x-axis shows the different data sets at different algorithms, and the y-axis shows the batch processing latency of 3 different data structures normalized to the AS data structure. The most prominent pattern from these experimental results is the different relative performance benefits of different data structures for different categories of data sets. More specifically, we observed that for LJ, ORCUT, and RMAT, the degree-aware hashing is the worst data structure in terms of batch processing latency, whereas the AS adjacency list is the best one. On the other hand, for wiki and talk datasets, the AS is the worst data structure, whereas the degree-aware hashing is the best one. Further experiments show that the key difference between these two categories of datasets is their per batch degree distribution. For LG, ORCUT, and RMAT, their batch degree distribution is short-tailed or low imbalanced. On the other hand, for wiki and talk, their per batch degree distribution is relatively more heavy-tailed or higher imbalanced. This can be seen more clearly in the table on the right below, where wiki and talk consist of a higher max in degree or max out degree in the entire dataset, and also in one typical batch that is streamed in. For the second question, our key takeaway is that larger graphs benefit more from the incremental compute model. The results on this slide provide evidence for this observation. On the x-axis, once again, are different data sets at different algorithms, whereas the y-axis shows the ratios of the compute latency from the from-scratch compute model and the incremental compute model. As it can be seen that in general, RMAT, which is the largest data set in our evaluation suite, benefits the most from the incremental compute model. For larger data sets, the incremental model is more effective at saving computation-related work during successive compute phases in streaming graphs. Next, we want to understand the batch processing latency breakdown between the update and the compute phases. The graph on this slide, the x-axis shows once again the different data sets for different algorithms, and the y-axis shows the percentage of the batch processing latency which is occupied by the update phase. We show this breakdown across all the three stages of the execution, P1, P2, and P3. The main takeaway from these results is that the update phase is actually non-trivial in streaming graph workloads. In many cases, more than 40% of the latency comes from the update phase. Next, we move on to section 4, where I will talk about the architecture level characterization of graph update and graph compute phases. For these experiments, we use the incremental compute model, and we use two data structures which are the best for the corresponding dataset categories. So for LJ, ORCUT, and RMAT, we use the adjacency list AS data structure. We call this category S-tail, which stands for short-tailed. For wiki and talk, we use the degree-aware hashing data structure and call this category H-tail, which stands for heavy-tailed. The profiling tool that we use for these experiments is the Intel Processor Counter Monitor. For the hardware level profiling, we want to answer two key questions. The first one is, how do update and compute phases utilize the various architecture resources? And the second question is, what influences the architecture resource utilization of the update phase? For the first question, our key finding is that the update phase in general exhibits a lower utilization of architecture resources. To support this observation, we show on this slide the resource utilizations from the perspectives of core scaling and memory bandwidth utilization. For the core scaling, we basically show that as we increase the number of physical cores, the update phase shows good performance scalability up to about only 8 to 12 cores. In contrast, the compute phase shows good performance scalability for up to about 20 cores. For the memory bandwidth, for both the categories S-tail and H-tail, we observe that the update phase uses lower memory bandwidth than the compute phase. For the second question, our key finding is that the underlying structure of the graph's input batches influences the resource utilization of the update phase. Once again, we support this observation using the core scaling and memory bandwidth experimental results. For the core scaling, we differentiate between the performance scalability of the update phases of the S-tail category of datasets and H-tail category. Compared to the S-tail category, we observe that the H-tail update phase shows even poorer scalability. In fact, the performance scalability for the H-tail category dies beyond 4 to 8 cores. In comparison, the S-tail update phase shows slightly better performance scalability up to a higher number of core count. For the memory bandwidth, we observe similar results. The S-tail update phase utilizes about 13 to 32 gigabytes per second of memory bandwidth. In contrast, for the H-tail update phase, the memory bandwidth utilization is extremely low at about 5 gigabytes per second. These architecture level findings show that the update phase possesses lower levels of thread level parallelism. More specifically, the H-tail category of datasets, their input batches are heavy-tailed or more skewed, and therefore they possess even more inherent parallelism bottlenecks. And therefore, their input batches during the update phase are less capable of leveraging a large number of core counts or larger memory bandwidth. To conclude, we have shown that streaming graph analytics is important in many application domains, and it possesses key differences and unique challenges when compared to static graph analytics. However, there is a lack of systematic software and hardware studies in the prior work. Motivated by this shortcoming, we have presented three contributions. The first one is SAGA-Bench, an open source benchmark. The second one is a systematic software characterization to provide insights on the best data structure, best compute model, and latency breakdown. And the third one is architecture level characterization to study how the two key phases, the update and compute phases in these streaming graph workloads, utilize different architecture resources. Thank you for listening.